So today I'm going to talk about the applications of sound VIs in LabVIEW. So basically we'll be talking about how you can create different applications related to sound in LabVIEW. So I am Ashish Sajwan from I work as an applications engineer in National Instruments. So in the next half an hour or so, I'll be talking about different applications of sound VIs. Then I'll be showing you how LabVIEW can help creating an application related to sound. So we have different VIs and pallets related to it. So I'll be showing you that. And at the last, I'll show you some demos which I've created, and I'll show you how to make an application, how simple it is to make an application related to sound in LabVIEW. Okay. So what is sound? So sound is nothing but a mechanical wave that is an oscillation of pressure transmitted through some medium such as air or water, composed of frequencies that are within the range of hearing. So when I say within the range of hearing, here as it concerns us, so I mean to say range of hearing of humans, right? 20 to 20 Hertz, right? Now let's talk about the applications of sound. What all applications can we do related to sound? So a typical example can be as simple as a power spectrum wherein you do an FFT, right? Or a tone measurement wherein you calculate the harmonics of a speech signal, right? Or it can be something as complex as a speech recognition or a reverberation or stereophonics or telephony. So an example of speech recognition can be wherein the system, your system, is able to recognize what you have said. So there can be two types. Either it can be a very generic system which recognizes whatever I say, or it can have a database of some commands which I've already fed into it, and it can recognize only those commands with more accuracy. So a typical example can be a wheelchair which is guided through speech, or a DC motor which is guided through speech, right? Now another example or another application can be a reverberation wherein you get to hear the echoes of the sound, right? Or a stereophonics, which is nothing but an audio illusion of sound, so that you get to feel that there is a surround sound, or the sound is coming from different directions. Now even in telephony, this is also an application of sound wherein you transfer the sound signals to a long range. You transmit them for long ranges of distance. So this is just a few examples of sound. You can have many more. The list is endless. So let's talk about LabVIEW now, because this demonstration or which I'm going to show you, or this presentation, is more of LabVIEW, right? So I'll show you how LabVIEW helps you developing these applications related to sound, right? So what does LabVIEW provide me to program or to code or to develop some application related to sound? So I have this graphics and sound palette. So it is there in the programming palette in the block diagram. If you right click on your block diagram, you will be able to see there is a graphic and sound palette. In that, if you go to sound, there is a sound subpalette inside it. If you go into that, so it is further divided into output, input, and files. So what do I mean by output, input, and files? So output is nothing but it uses the sound output VIs to configure and control a sound output device. Now what is a sound output device? Sound output device can be something like a speaker on your system itself. An input can be wherein you are giving an input of a sound signal. For example, you are using your microphones. And the third is files. Files is nothing but file handling of the sound files which are there present in your system. Now these files can be either audio files which you are recording on the fly, or they are like pre-recorded files, or those files which you have downloaded from somewhere and they are present in your system. So that they are sound files which are there present in your system on your hard disk. So output and input is more of, you can say, a dynamic data, right? And files is something which is present on the hard disk itself, right? Let's see them one by one. So sound input palette has acquire, which is an Express VI. You can make out by the blue background of the Acquire VI. So Acquire is an Express VI. So when I say an Express VI, it means that it is quicker to use. So if you want to reduce your application development time by a great extent, you can use an Express VI, something like Acquire VI in this. So Acquire VI is nothing but a combination of all the low-level VIs which are there on the second row. So it just makes your application building very quick. And but if you want more flexibility and control over the application, then you should go for the low-level VIs which are present on the second row, which are nothing but configure, which is to configure whether configure the input application. For example, you want to configure which particular microphone array you want to use to take the data in, or you want to configure what is going to be my sampling rate, right? And then we have start, which is nothing but starting the acquisition, then read, from which you can extract the signals, then stop is to stop the acquisition, then we have clear to clear the resources, right? So this is as far as sound input palette goes. Now after that, if we talk about sound files palette has these simple VIs. So there is no Express VI in this case. Sound files palette consists of only low-level VIs. It has simple read, simple write, to simply read and write to the files, right? Read from the files or write to the files. It has an open, wherein you open a file, so you open a resource, and then there is this info file, so you get information about that sound file. You can read that file, you can write to that file, or you can close the resources. So what is the difference between simple read and write? Simple read and read, or simple write and write. That is just that read is more advanced, you can say, from the simple read, right? Okay. Sound output palette. Sound output palette consists of all these VIs. So here also we have an Express VI, which is play waveform. So play waveform is an Express VI which takes care of all the low-level VIs which are there on the second and third row. It configures, it gives you a dialog box in which you can configure the task, the output task, and you can set the weight, or you can set the volume. You can do anything, whatever you want to do, right in the dialog box itself. So it kind of takes care of all the low-level VIs. So what are low-level VIs we have? If you want more flexibility and control over your application, so let's see each of them. What do they have to offer to us? So first of all, let's talk about play waveform, which is an Express VI, which is clearly, you can see it clearly from the blue background of it. So we have this play waveform Express VI, which does nothing but plays the data from the sound output device using finite sampling. So it just plays the waveform, right? Now what is good about it is that it will reduce the application development time to a great extent, because it is just one single block. So with one single block, you can configure how you are going to output the data through your speakers or through your headphones, right? And you can configure the sampling rate, you can configure which speakers or which headphones to give output from. And it automatically configures an output task, and it clears the output task after the output completes. So you don't have to really care about clearing all the resources, which you have to do when you use low-level VIs. Now, if you want more control or more flexibility over your application, so you'll have to go for low-level VIs. So we'll talk about them one by one. We have sound output configure VI, which is nothing but a configuration VI wherein you can configure the different parameters for the sound output. So you have number of samples per channel. So you can configure how many samples you're going to read, then the sampling mode, whether you want it to be a finite or continuous. Then you can give the device ID for the computer to know which device exactly it is going to send the output from, right? And then we have sound output write. So sound output write is nothing but it writes the data to a sound output device. Okay. So herein you have to give the task ID. Task ID is nothing but the reference for that task, right? you can see on the configure VI, which is the first VI. So that gives an output of the task ID, which is nothing but the reference to that sound output task, right? So that is an input to the sound output right VI. Now, if I talk about start VI and stop VI, so they do nothing but they just start the playback from the device or they stop the device from playing sound, right? So it is just starting and stopping. Now, if you want to, if your application is such that you want to stop the playback of the song at or of the sound at some particular instant of time, then you can use something like a sound output wait VI. So it does what it does is it waits until all of the sound is played by the output device. Now you can configure it that whether you want all the sound to be played, or you want it in fraction, like you want some portion of the sound to be played before this and some after that. So that you can configure. Now sound output info is nothing but it is just giving you the information about the sound output. For example, it is giving you the volume, or it is giving you whether it is still playing or not. So let's say you want to do something like if it stops playing or whether when it completes playing, so you want to do something else, right? So you have that Boolean output from it, which you can use to do or trigger something else, right? So it just returns the information about the current state of a sound output task. Then we have the sound output clear VI. So what it does is, as the name suggests, it clears down all the resources. So it stops the device from playing sound. It clears the buffer. It returns the task to the default state, and then it clears the resources associated with the task. So even if you don't use a stop sound output stop VI, you can just directly use sound output clear VI, which will just clear the resources. So if you want to just stop the sound, you don't want to clear the resources, you want to use it sometime later, then you shouldn't use the sound output clear VI. If you want to release the resources as well, then you should use sound output clear VI. Then there is something like set volume VI. So as the name suggests, you can set the volume. What is going to be my volume of the sound output, which is going to come from the speakers or the headphones. Now finally we have the main VI, which is play sound file VI. So it is, you can say, a contemporary of the Express VI which we have seen, but then no, Express VI takes care of all the other VIs also. This VI is just for playing the sound. So what it does is you have to give a path of the sound file to it and the device ID from which you are going to take the output from. So what it will do is it will just open that file and start playing it immediately. Okay, so we have talked about different VIs which are present on the sound output palette. So let's talk about the demonstration which I'm going to give you, or the an application which I'm going to share with you today. Let's talk about audio players. So all of you must be aware about audio players, right? So there are different audio players in the market today, and many of them are from open domain and many of them are from products oriented companies. So for example, we have Windows Media Player from Microsoft, and for example, we have VLC Media Player, we have Pod Player, Winamp, we have KMP, Jet Audio. So we have, and these are just to name a few, right? We have a number of audio players in the market today. And what if you want to make an audio player of your own, or a custom audio player you can say, wherein you can tweak whatever you want, or you can set it as you want. Let's say you don't want a button, so you just don't keep it there, or you want some extra functionality, you want extra control over how the sound is going to be played. So you can just program it using that. You can just program it accordingly using LabVIEW. So let's look into how we can do that. So this is just a snapshot of a custom audio player I made using LabVIEW. So let's open it up. So I have an audio player here. So let's see what it does is, I have a playlist here which is nothing but the path to the different songs which I want to play. So herein I have only 2 songs from Papo, and I have these simple buttons here. I have an audio player here which has simple options like play, stop, or next, previous if you want to go to the next track, or if you want to switch on to the previous track. And then I have switch off, using which I can just switch off the whole audio player, right? So let's see how it works. So what is the underhood programming which I have done? It is quite simple. You can see from here. So I have these 4 Boolean controls: next, previous, play, stop, which I had shown you on the blog, on the front panel. So I made a Boolean array out of it, and I'm searching the 1D array for a true value here. Okay. I'll have this context help open so that you can see what all functions I've used. So this is a search 1D array wherein I have searched the 1D array for a true value, so that I know right now which button has been pressed, so that accordingly that particular case gets executed. So I have a case structure here. This is a case selector terminal, and accordingly that particular case will get executed. So and then I have the playlist as an array of strings. So what are the strings here? That are nothing but the path of the different songs which I'm going to play, right? So, and I'm changing from one song to other using the indexing. I'm indexing the array here. I'm converting that string to path here, and I'm giving it to the play sound output, right? Okay, so let us see what is going on inside the case structure. So when it is in play mode, you can see it is a second, right? So it is in the play mode. So when it is in the play mode, I'm configuring the task here. Then I'm playing it. I'm starting it, and then I'm playing it here, wherein I'm giving the path from using indexing on that array of strings, and I'm handling error also here because I'm propagating the error inside this while loop, and finally I'm going to take it out and give it to an error handler, simple error handler. Okay. Apart from that, since this is going to be continuous process, I'll have to pass on the reference of the task also, that I'm doing using shift registers here, right? And moreover, I have to keep track of which track is currently playing, right? Which song is currently being played. So that I'm doing using shift registers on the index. Okay, so let's move to what I've done for next. So for next, you can see it is the whole VI or the whole code snippet inside the case structure remains same, other than this increment function here. So I've used an increment function which will do nothing but just increment the index of the song so that I get the next song. So obviously for the previous song, I do a decrement function here, right? So play function we have already seen. So let's talk about stop. So how, let's talk about default first. So in default, when none of the buttons are pressed, so it will just keep doing whatever it was doing. So if it was stop, it will just keep on, it will just keep on getting stopped, or it will just stop there. It will not do anything. If it was playing, so it will just continue playing, right? And for stop, I have this top VI here, and then I'm clearing the resources, because here I have to clear the resources as well, right? Okay. So let's run this. Let's see what happens. Okay. Okay. Let's see what happens. When I run this, so you see there is this play option. If I play this, so my first song from the Papo tracks, I have 2 tracks here, Gia, that gets started, right? Okay, if I switch on, if I want to switch on to next track, which is verse, I'll just switch it on from here. So there's the next track. Right now I have only 2 in my playlist, so I can't do a next here. But the idea is, I think, will be very pretty clear by now. So if I just want to switch on to the previous track, I'll use this. Right. If you want to stop it in between, you can just stop it using this. Right. And let's say you want to just switch off the whole demonstration, or you want to just switch off the audio player, right? So you can just switch it off, so it comes back, right? So let's have a quick run again. So I run it here, I get this screen, I get this audio player, and now you can customize the audio player more. I have not customized it more, so you can customize it obviously. So if I play it, it gets played. I can do whatever I want. I can stop it something, or if I play it, I can do a next, right? I can stop it whenever I want. I can just switch it off, right? So that's how it works. And I've told you the logic also. Okay, so let us talk about, let us make a VI here, which is nothing but Talking Tom. So Talking Tom, I have made one VI also. So this is the VI. I'll first explain you this, and then we'll make it make a quick Talking Tom here itself. I'll make it in front of you. So this Talking Tom, this face will be very familiar to you. It's an Android app, right? So let's see what is the logic behind. And to your amazement, the logic is very, very simple. So all you have to do is you have to tweak the frequency at which you are acquiring the signal, right? I mean, the input signal has some frequency. So when you speak, you have some frequency attached to your speech. So you have to just tweak that frequency, and you have to just play it back. So it's just record, do some analysis. What is that analysis? You just get the DT of it, or you just get the frequency, you tweak the frequency, and then you play it back. It's as simple as that, right? So I've used some express VIs here. So here there's an acquire sound. So it is an express VI which enables you, using just one block, you can just acquire the sound, right? Then we have power spectrum, which is giving you the FFT, the frequency domain signal. So your signal, which was in time domain till here, I have converted into frequency domain so that we can know how much I have tweaked the frequency. Now what I'm doing here is I'm converting that dynamic data into a single waveform, and then I'm extracting the components of the waveform. This is a Y array, which is nothing but the amplitude, an array of amplitudes. T0 is the first time, so out of the whole array of the time, so this is T0 is the first time in the waveform. Dt is the time interval between consecutive samples in that array. Then what I've done is I've just elongated that dt. So in this particular example, I have done it twice. So that means my frequency will be halved. So I'll be getting a more bass sound, right? After that, I've just played the waveform using play waveform express VI, and then again I'm doing an FFT so that I know what is the frequency, what are the dominant frequency ranges which it has gone to. and then I'm just plotting it on the waveform graph. Okay, so let's quickly build it also. It is very easy to build. So you can just see the response of it right now. So I have this acquired sound here. Okay, duration, let's say I want to do it for 3 seconds. Right. Now, if I want to do a play waveform, I'll do it here. Okay, so the sound is going to come through the speakers right now. Okay. Now I want a power spectrum. So I have a power spectrum here. Okay. I want it as a spectrum only. Okay. I want another power spectrum, which I'll keep it somewhere over here. Oh. So I'll keep it somewhere here. Okay. So this is from dynamic data converter. So I'll just make it a single waveform. Okay. Now I want to get the waveform components, right? So let's get the waveform components. T0, dt. So I've got all these waveform components. Now other than that, what I want is I want to finally build another waveform, right? After tweaking it, I want to build another waveform of it. So that I'll do here. So we don't have to do anything with the amplitude as such if we want to just change the frequency, right? Other than that, I want to multiply it. Now you can multiply it with anything. You can even multiply it with a fraction, but just make sure that your sound card doesn't crash, because sometimes if you make a sampling rate like very high, then in that case your sound card may not be capable of getting that much sampling rate. So it may not support that high sampling rate. So in that case, you should just make sure that you've done this. Okay. Let's give it also a single waveform. Okay. Now I really want to see what is the spectrum. Sorry. And I want to see the spectrum in this case as well. So let's see the VI once more. What I've done is I've taken the sound here and I've converted it into a waveform. I've extracted the waveform components. I've halved the frequency, or I've doubled the time intervals, you can say, and then I've given it to I'm again doing an FFT on it, and I'm playing that waveform also, right? and these are just to compare. So spectrum 2 is, you can say, the talking Tom response, and this is the original spectrum. So let's run it. Hello. So were you able to listen to it? Hello, this is Ashish. So I told you something, right? That you can even give a fraction here. If I give a frequency fraction here, let's see what is happening. Hello, this is Ashish.
Hello, this is Ashish.
So you see the frequency got increased, right? Because I reduced the DT here. So that's how it works. So just make sure that don't just go on reducing the number here, or go on reducing the go on increasing the frequency, because you are essentially taking all the samples. So in that case, you'll have to sample it at that rate. So just make sure that your sound, it is within the limits of your sound card, right? Okay. So this was my custom audio player. This was the Talking Tom which I made through LabVIEW. So the contest of the week, we will soon post you. About the contest of the week. So I'll just brief you about it. So the contest for this week is to make an audio player wherein you have the flexibility of not just going to the next track or previous track, you have that flexibility of fast forwarding it, or the same case with the reverse also, right? So let's say you want to go to a specific point, or you want to fast forward through a song, you don't want to listen to a specific section of the song. So you have that option, right, in the players, that you can fast forward it, or you can reverse it back, right? So same is the case. So same thing, you have to create a logic. Rest of the code will remain same as my code, which I've shown you today, and just add this functionality in it. So that will be the contest of this week. Okay, and so there was no winner as such. So extending learning and participation, you can extend your Webcast Wednesday learning experience on LabVIEW. So LabVIEW enabled is nothing but an NI India online community. So NI India community, it is a community, it is a single network of students and industry professionals and academicians which come together to create discussions, exchange and share resources, or generate content on applications or NI technologies, as well as the industry trends or other third-party technologies. Okay. Now, apart from the live online interaction during the webcast, an extended discussion and a contest on the topic will be carried out for an entire week by the presenter on LabVIEW enabled, which is the NI India community. Now you can watch the previous episodes of Webcast Wednesday also, because they are archived in the website, and you can get your queries from the sessions, and LabVIEW, you can resolve that, and you can participate in the weekly contest and win up to 50% discounts on National Instruments certificate examinations. If you attend 20 sessions, You can win a free CLAD attempt. Okay. Okay. If you have any questions related to LabVIEW or related to the presentations I've shown you today, you can just ask to the consultant sitting with me. I hope you enjoyed it. Okay, so let's see you next week, Wednesday, same time, which will be 4 p.m. to 4:30 p.m. Thank you.